Now I'm going to talk about what's called Le Chatelier's principle. So chemical equilibrium is a fact of life. If you mix reactants and products together, you are always going to reach equilibrium. But we still want to be able to control what that looks like. And what I mean by that is, what is say you may have more products than reactants, but which products do you have? What is the balance between the different components of the reaction? Say you're trying to make product. If you're dealing on a scale of tons of product, if you're losing 0.1% of unreacted reactants, that's a lot of money you're losing. Or say you have, a reaction where you're going to make, it's reactant favored, not much product exists, but it's really nasty stuff. It's lead ions or something like that. You want to ensure that you're not running that chemistry. How can you run this chemistry such that you prevent that from happening? Say you also may want to have like a switch somewhere in the middle, one of those K equals like say 20 reactions that you can have it kind of switch back and forth on off between reactants and products. The thing is, K is a constant, right? If you have a given temperature, a given reaction, K is just a number. So you can't change that. You got to work within the bounds of equilibrium existing, but it's not always going to look exactly the same based what is actually part of that K. The relationship of that ratio, products to reactants, is the same, but what are the reactants? What are the products you have? So if I have an example, N2 plus 3H2 gives me 2NH3 Haber-Bosch process synthesizing ammonia. Very big industrial chemistry. So say I'm at equilibrium, right? I have some sort of initial equilibrium, which is my concentrations are all constant, right? They're constant with respect to time. Well, what I could do is I could just add some extra reactant, right? So that's what this little bump right here is. You just add some extra reactant. At that point in time, you now are not at equilibrium. Right? You are not at equilibrium because you have more N2. The previous amount of N2 was at equilibrium. And so as a result of that, the system is now out of equilibrium and will need to evolve to get back to equilibrium. We could calculate a Q value for this and we could look at that. But we also just know that what I added was a reactant, meaning I have too many reactants. So the forward reaction is going to happen. And what I'm going to do is I'm going to make product. So in the end, by perturbing equilibrium, by adding in some extra reactant, I can see that effectively what happened is I increased the amount of product. So I'm still at equilibrium. We can see that over here in the new equilibrium, everything is a constant amount out here. Everything is a constant amount in the new equilibrium, but they are flat, right? Those are flat concentrations with respect to time, and that means I'm at equilibrium. And so what's happening is I just have more ammonia at that equilibrium. I also have more N2 and less H2. So the equilibrium looks different, but if what I care about is making as much NH3 as possible, this would be a desirable change. So this is an example of what I mean by controlling equilibrium to have it look like what you want. You're getting more NH3 out, more desirable product. So another reaction we could look at, say for example, acetic acid plus methanol gives me methyl acetate and water. I'm going to do this reaction. I'm trying to make methyl acetate. That is the product that I'm trying to make. I'm going to use that to make some plastics. So I run my reaction and I get a mixture at equilibrium. Okay, so I have a mixture at some mixture at equilibrium. Not doing that great. I only made 4 methyl acetate molecules. Not good enough. I'm trying to sell this stuff. So I add some extra reactant. I now have these new acetic acid reactant molecules. My system is no longer in equilibrium because I was just at equilibrium. I've only added one component. I can't be at equilibrium anymore. So forward reaction is going to happen. Right there, it reacts with some of the methanol that was already in there. Boom, and boom. And so I make more product. Okay, and other reactant goes away. And what happens is I'm now at a new equilibrium. K is the same, so relative amounts of everything. Everything stayed the same, my relative ratios. But I have more methyl acetate. What I was trying to make was methyl acetate, and that's all I care about. So I have 6 methyl acetate molecules. That's a 50% increase. That would be a benefit to me. So this is one of the things that we can do to drive equilibriums. We can force equilibriums to shift. We add only one reactant and we make more product at the expense of the other reactant. And generally we can choose, we add more of a bunch of extra of whatever's cheaper, right? We use the cheaper one and then we get as much product as possible. And so this idea that the position of equilibrium shifts to relieve applied stress, that is Le Chatelier's principle. So when you have a system at equilibrium and you do something to perturb it, to take it out of equilibrium, in this case, we are increasing the concentration of one of the reactants, right? You've increased the concentration of reactants. You can think that's what makes it not at equilibrium, the fact that you have extra of this acetic acid. And so you have extra of the acetic acid, so the equilibrium will respond to remove that acetic acid. And that's why you get a shift to product side. Okay? And so this is the underlying idea of Le Chatelier's principle, that equilibriums shift to relieve applied stress. You add in extra concentration of any species, the equilibrium will shift to decrease that amount that you added in. And in this case, that was to product side, which makes products. So this would be an example of we're trying to drive this process. We want to make more ethyl acetate. Add more of one of your reactants, you're going to start making more and more ethyl acetate. Removal of a component can also shift equilibrium. So, for example, H2O liquid becomes H2O gas. At 25 degrees Celsius, K is less than 1. This is the evaporation of water. We know this doesn't become favored till above 100 degrees Celsius. So at 100 degrees Celsius, K is equal to 1 for this. And above 100 degrees Celsius, we would expect K to be greater than 1. But below room temperature, it's less than 1. So this is a reactant favored equilibrium. So we would expect that means it doesn't really happen. If you have liquid water, it will stay liquid water. But if you leave a cup of water out over time, it eventually goes away, right? It may take some time, but eventually you have no water left, which would imply that this process goes all the way to products, right? Because if you start with only reactants, right? Say you start with only reactants, eventually you have only product, right? That's an empty cup. And so the equilibrium is favoring water, but there's a full conversion of reactants to products, right? So something is going on here. So if we think about a molecular view, we got a bunch of water molecules in the liquid, right? And they are sitting in the liquid. And we know that some of them are going to leave to enter the vapor. That is establishing an equilibrium, right? In the equilibrium, I have reactants, all my liquid water molecules, and a little bit of product, a little bit of that gas phase molecule. So at equilibrium, we'd have both of these. So this right here, this system would be at equilibrium. Most of the molecules are in the water. Huge majority are in the water, but some are out there in the vapor. The thing is, your cup is open, and that's a gas molecule, so it escapes. Now, this system is not in equilibrium. There's no more product molecules, so the system has to respond. You have decreased the amount of product, right? It's empty. It's a goose egg up there. And so the system has to respond to replace it. So another molecule goes into the vapor. Now, again, the system is at equilibrium. Most of the molecules in the liquid, one or two small handful of molecules in the vapor phase, but again, that can escape. So over time, you make equilibrium with molecules going down to the vapor, but slowly but surely they all just keep escaping out away into the bigger room, and eventually the water evaporates, right? It's just the liquid is molecules keep leaving the liquid to keep reproducing this product to reestablish equilibrium, but those product molecules keep leaving. Right? So you keep going again and again. And so this may be an example of like a cup of water, but this is functionally how a lot of chemistry is also done. If it's not reactant favored or product favored, you just remove the products from the system little by little. And that way they just keep getting replaced a little bit at a time, a little bit at a time. It's a slow process. Evaporating water is really slow, but this is an example of a process that is not favored that equilibrium constant is small. This is very much a reactant-favored equilibrium. But over time, because those products are escaping, they need to be replenished. They need to be recreated, and you can get a full conversion of reactants to products in a way that is not desired, for a process that is overall not desirable. Of course, if you cover the cup, it does reach equilibrium. Some molecules do exist above the liquid. We know that that is called the vapor, and that's why you get a vapor pressure. So we talked about this before. We can understand that idea that was purely based on intermolecular forces previously from an equilibrium perspective. There is just an equilibrium that has to exist between the liquid reactants and this gas product up here. There has to be some vapor. There will be some vapor out there. All right, so we want to be able to use these ideas, make predictions as to how equilibriums will respond to perturbations. So I got PBr3 plus Br2 becomes PBr5. We're going to make some changes to it. So first, I'm going to increase in the concentration of PBr3. So I can see that PBr3 is a reactant. If I increase the concentration of a reactant, the system will respond away from that. And so that would be a shift to products. Whenever I increase a reactant, I expect to see a shift to products because there's too much reactant, so the system will respond to get rid of it. If I increase the concentration of PBr5, that's now a product. I increase the concentration of product. The system shifts to reactants to deal with it, to get rid of that, to make it go away, right? We want to get rid of this excess product. We're going to make more reactants now. Finally, we have a decrease in the concentration of PBr2, or sorry, just Br2. So we're going to decrease Br2. And so we can see what we're doing there is we're removing a reactant. So if we're removing a reactant, the system needs to respond to replenish that reactant. So that would be a shift back to reactants. So we would expect that overall the PBr2 amount would decrease and the PBr3 amount would increase. So you would replace the lost Br2 at the expense of the PBr5, those product molecules, making additional PBr3. So we can think, what do I not want? What do I want? How can I add things in, remove things to drive the changes that I want to cause?
Participation 215, question 4. What effect would each of the following have on the equilibrium for the reaction of cobalt 2+ reacting with 4 chlorides to yield CoCl4 2-? So kind of a complex ion here, but it's cobalt cations reacting with 4 chlorides to give you this cobalt chloride ion. So the three things are addition of cobalt 2 nitrate to the solution, addition of sodium chloride to the solution, and addition of silver nitrate to the solution, which reacts with chloride to form silver chloride solid. This is the fourth question on participation 215, due Tuesday, February 15th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Basically, just what effect would each have on the equilibrium for the reaction, adding cobalt 2 nitrate, sodium chloride, and silver nitrate. Silver nitrate does react with chloride to form silver chloride solid. We want to spend a little bit of time talking about Le Chatelier's principle, understanding Le Chatelier's principle from the perspective of equilibrium constants, because we know equilibrium is still going to be governed by the equilibrium constant expression, right? What the relative quantities of everything are is still going to come from Kc. So how can we understand what we've predicted and what we do observe? We're using Le Chatelier's principle. How can we explain it with our equilibrium constant expression? So we have our acetic acid and our methanol reacting to make our acetates. And so we have our mixture, and we know it's the relative amounts of everything are going to be determined by our Kc value. And this Kc isn't going to change if we just start adding reactants and products. I throw some reactants in, nothing happens to the value of Kc. That hasn't changed. But I am no longer at equilibrium. So the value of Kc hasn't changed, and the fact that my system needs to eventually reach equilibrium is still true, but when I add more reactant, the system is no longer at equilibrium. So what matters is the calculation of the reaction quotient Q. I added a little bit of reactant, so I can kind of imagine that as like plus delta, plus whatever the change is. It doesn't even matter how much I added because I'm adding a reactant. So I'm always going to add a little more to one of my quantities that's in the denominator, meaning the denominator is a larger value. So if the denominator is larger in my Q, that means Q is now lower than K. If my reaction quotient Q is smaller than the equilibrium constant, the reaction is going to shift a product to get back to equilibrium. So the equilibrium constant and all that hasn't changed. I've just taken the system out of equilibrium. And now it wants to get back to equilibrium by shifting to products. I can also use this kind of idea to kind of think about what would happen if I add something that's not in the equilibrium constant. So for example, dissolving lead to chloride. I know that this tends to, not really go to products. There's not a lot of product that's formed, but some is formed. If I add more solid reactant, I'm not going to dissolve anymore because that solid reactant, I add more solid reactant, Kc equilibrium hasn't changed. The reaction quotient is still just going to be based off these product values because those are what are actually dissolved. So it doesn't do anything if I just add more solid reactant. It's not going to yield any sort of shifts. Nothing's going to cause anything. So this is generally true for adding solids and liquids. Except when you're adding water in a reaction that's doing aqueous chemistry. Because what ends up happening is, so say, for example, this reaction where you add water, it is a reactant, but also you can see it kind of cooks into everything else because everything is aqueous. So what ends up happening is if you add water, you dilute everything, right? You're diluting everything, you're changing their concentrations. If you change the concentrations of everything, you end up affecting the value of the reaction quotient. So you can imagine, let's just imagine we halved everything, right? You like doubled the water, you added extra water. So you doubled the water, concentrations all decrease, you figure it out. Q is now less than Kc, so your reaction quotient is below Kc. The reaction is going to shift to products, which is exactly what we would expect if instead of going through all that, we just said, I added water, that's a reactant, I'm going to shift to products, right? You shift to products because you added a reactant. So we can explain it using the equilibrium constant, but that's why we can just kind of think about the reaction, or the Le Chatelier's principle kind of characterization of you added a reactant, it needs to shift to products. One final thing we want to think about, how would the equilibrium of reaction shift if a catalyst is added to the reaction mixture? So we're adding a catalyst. We know that affects the kinetics of a reaction. It doesn't do anything to the equilibrium. So equilibrium is once the kind of equilibrium is reached, what will be there. Catalyst just means you reach equilibrium faster. So you reach the equilibrium faster, but the relative amounts won't change. It does not affect the value of Kc. Kc, if you think about it, is just all about reactants, products, starting thing, ending thing. No transition states, no mechanisms, no nothing like that. So catalysts don't affect equilibrium. You get to equilibrium faster, potentially a lot faster. You might reach equilibrium. You might not reach it without a catalyst, but it doesn't change what equilibrium looks like. All right. Participation 215, 4 questions. It was a long set, so I won't keep you here, but it was a long set of videos, 4 questions on that participation. You got the midweek due Wednesday about this first start of the chapter, 13 stuff, and then the lab chemical equilibrium. We'll take a look. We'll see what equilibrium looks like. It's really cool. Get to see some of this stuff in action. Otherwise, I'll see you in the second half of the week for the rest of chapter 13. Otherwise, enjoy the rest of your day. I'll see you later this week or in lab, both, hopefully. Bye-bye.